Okay, everyone, good afternoon. Welcome to our 7th lecture for the Postgraduate Dynamics course MSD 780, and then also the 3rd lecture in our Applications Example study theme. Today we're going to continue with the cart example. Now, before I do that, just to give you a quick review of what we've done up to now for the application examples. We've looked at the two suspension systems, the double A-arm or the double wishbone suspension system, as well as the McPherson suspension, both of which introduced us to the idea of a point-to-point force or a spring damper force, which is a very common compliance element that we have when we consider dynamic problems. And it also introduced us with section 8.1.2, the McPherson suspension, to the idea of composite joints, where we can remove certain linkages from a system in an effort to reduce the computational effort, and then combine the joints that act on that specific link or body. Now for the cart itself, we looked last week at cart A and B, both of which were focused around the inverse dynamics of a cart. So we specify some sort of a displacement or angular position on a system, and we want to measure what the forces, so the loads or the torques are on the system, as well as the overall motion of the system. Today we're going to look at cart C and D. Now these two carts are now going to use a forward dynamics approach, in which case we are going to specify some sort of a torque on the system, and we now want to go and measure what the motion output of the system is. So forward dynamics approach is always when we specify the load or the torque on a system and we measure its motion as an output. So jumping straight into cart C, we are going to look at this as a variation of the previous cart models, where an applied torque has now replaced the driver constraint on the rear wheel. Remember that when we work with driver constraints, we usually define this as an addendum to our kinematic constraints in the system. So we use the infuncts file when we work in DAP-BC. We set up our function over there, and we can define the driver constraint as an actual joint, either a relative rotation or a relative translation driver under our in-joints file. However, as soon as we now start working with forward dynamics problems, we can make use of a user-defined force when we don't have a stock standard torque or a stock standard force that we specify on the system. And this is what cart C is going to focus on now. In fact, we assume that the torque is then generated by an electric motor where we have some sort of a torque speed characteristic. And this is then shown in figure 8.12 over here. So we have the torque on the x-axis, which varies from 0 to 20 Newton meters. And then on the y-axis, we have the angular velocity, which varies from 0 to 4 pi radians per second. Now, to better understand this, we can go back to PMD section 4.5.2, which deals with a motor and a driver. A rotary motor can be included in a multi-body model between two bodies about the axis of a pin joint. In most applications, one of the bodies is the ground, as shown in figure 418A. So in this case, we specify a motor on this crank arm over here, but in essence, this motor is then acting between this grounded point over here and then the point that we have on the body itself, so the link itself. So it's acting between body 0 and let's call this crank arm body 1. Now a rotary motor applies the pair of torques on the two bodies that are equal in magnitude and opposite in direction. So we treat it very similarly to what we would for a reaction force, in the sense that we apply Newton's third law to both of the bodies upon which the motor driver is acting. An idealistic representation of a motor with a known torque would be for the motor to generate a constant torque, or a torque being a function of time. So for example, the torque may follow a nonlinear function, in which case we can simply say that the torque is then expressed as t in brackets small letter t, which simply means that the torque is now a function of time. In a more realistic representation of a motor, we should consider its torque speed characteristics. So for example, if we look at figure 4.18b, we can see a typical torque speed curve for two DC motors. In the case of the linear line that we have over here, the solid line, that is for a permanent magnet motor, but we can also have some sort of a non-linear relationship between the rated torque and the rated speed. And this would be something like a compound wound motor that we have, and that is shown in these dashed lines over here. Now, either function shows that the torque varies with speed. So as the speed increases, the torque drops, and vice versa. Whether the torque is assumed to be a constant or a function of time, or to follow known torque speed characteristics, since the amount of torque can be determined at any given time and speed, we may consider such models in the category of an applied force or torque. And that is now where the user-defined force comes into play when we work with DAP-BC. So we create what we call a user_force.m file. Okay, so in our case, the motor represented by the torque speed curve, shown in figure 8.12, can provide a maximum torque of T max equal to 20 Newton meters at zero angular velocity, and can also reach a maximum angular velocity of 4 pi radians per second when there is zero load or zero torque on the system. And this is simply shown over here in figure 8.12. So to find an expression for omega motor, we simply consider the relationship for the linear line that we have over here. So y is equal to mx plus c. We go and calculate the gradient. That will be T max, it will be 0 minus omega max, because it's y2 minus y1 divided by x2 minus x1, which is then T max minus 0. And if we simplify that, we get this minus omega max over T max, which is then our gradient of the line. And then we also just need to find its point of intersection with the y-axis. So that is simply 4 pi radians per second, or if we parameterize the problem, this becomes omega max. So if I write the equation for omega motor, y is equal to mx plus c, so then omega motor is equal to the gradient, which is minus omega max over T max, multiplied by T motor, which is then my independent variable, plus omega max, which is the intersection with the y-axis. And now I can just go ahead and do some manipulation of this expression over here, so that I can rather write this equation in terms of T motor. So then T motor is equal to the maximum torque that the motor can provide, multiplied by 1 minus omega motor over omega max, which is some sort of a speed ratio that we have for the torque curve. Okay, so with that in mind, we can then move on to exercise 8.9. And exercise 8.9 then says that we need to simulate the dynamic response of this model for 6 seconds. And we then also want to plot the angular velocity of the rear wheel versus time. Now you remember from last week, we looked at the cart bodies. We said the cart body itself is body 1. The rear wheel is going to be body 2, and body 3 is then the front wheel of the cart. So before we jump into the actual analysis, let's perhaps quickly run through the input files that we have for cart C. So starting with in bodies, this is the same as what we had for cart A and B. Just define the mass, moment of inertia, the coordinates, and the initial angle for each of these bodies. Then we also have in points, which also remain the same. So we have in total 4 points, 2 of the points which are located on body 1, which we use for the revolute joint, and in points 3 and 4, which are stipulated on bodies 2 and 3 respectively, and at their center of mass location as well. That's why SP local is equal to 0, 0 for both of those points. Once we've done this, we then also set up our in joints file. So we have the 2 revolute joints, which connects the cart to the 2 wheels at their center of mass. And then we also have the 2 disc joints, which ensures that the wheels can roll along the surface, but also applies a no slip condition to the wheels. So we have both an X and a Y reaction force, which is defined by these disc joints that we have over here. So once again, the same as what we had for cart A and B. Then in funct, in this case, is now going to be an open list, since we're doing a forward dynamic analysis. So we don't specify any driver constraints on the system. If we then look at in U vectors as well, this is also an open list, since we don't have any translational joints acting on the system. However, one of the files that have now changed is in forces. So in this case, we still have weight acting on the system, But we now have force type 2 as well, which is a user-defined force. As soon as I use the keyword user over here, it means I need to go and create this user underscore force.m file so that I can populate this user-defined force over here. And I've done that and created this user force. And this is simply where I'm now going to specify the motor torque. And as we know, this is not a standard or a constant torque that I apply on the system, so I can't simply use a force type T in this case. I actually have some linear relationship between the motor torque and the motor speed. So in order to accommodate this, I need to define it in the user force file that I have. So firstly, I just specify all of the properties that are given to me. So omega max I know is 4 pi radians per second, T max is 20 Newton meters, and then I just have to go and find omega. So this is simply omega motor, the current time steps rotational velocity of the wheel that I'm considering. So since I'm working with the rear wheel, I use bodies2.p underscore d. So this will then extract the angular velocity for that body. And for this case, I'm just going to consider the actual angular speed of the system. So I'm just going to use the absolute value to give me the magnitude of the angular velocity, which is just the angular speed. Once I have this, I can go and set up my equations. I simply say T motor is then equal to T max multiplied by 1 minus omega over omega max. And this is simply the equation that I got in this case over here. Once I've calculated this, I can then just do a quick check as well, just to make sure that if the motor torque that I've calculated is greater than the maximum permissible motor torque, then I'm going to set the motor torque equal to the maximum torque. And this is simply due to the limitation of the motor itself. We can't expect the motor to deliver more power or more torque than what it is rated for, or what its maximum torque is. So whenever I have a value that exceeds the maximum torque, I simply derive it back to T max. And this then ensures that the system isn't going to have any further load variation beyond the point where T motor is greater than T max. It sort of plateaus on the torque in that case. Right, now once that is done, now I just need to go and apply the actual motor torque to each of the bodies. So I'm going to start off with body 2. So body 2.n simply denotes the moment that is currently working on body 2, so the rear wheel. And that is going to be equal to whatever the moment is currently on the rear wheel minus T motor. So in this case, T motor is going to be a positive value because T max is positive, and I multiply this with 1 minus some ratio over here, which is smaller than 1. So T motor is going to be greater than 0, but I want to apply a clockwise moment to body 2, to the rear wheel, so that the cart is moving from left to right. And to do that, I simply minus the T motor value in that case. And in accordance to Newton's third law, I just need to remember to give the driver load then on body 1 as well, since this load is acting between body 1 and 2. So in that case, I simply say body 1.n is equal to whatever the current moment is on body 1 plus T motor. So a different sign, equal magnitude but opposite direction when it's acting on body 1. And that then fully defines the user force of the system. Then lastly, we can also just look at inanimate. So this remains exactly the same as what we had for cart A and B. Once again, have two animation points, points 5 and 6. We also have the shapes and the colors, the widths and the heights and radii of each of these bodies defined in animate. And then finally, we just set up our actual animation pane as well, with the X values ranging from 0 to 8, and then Y from minus 0.5 to 1 meters. Once we're happy with all of that, we can go to our command window, and now we can start running cart C. So to do this, I just type in DAP. It asks which model I want to run, so it's going to be cart C in this case. I correct the initial conditions, and then I'm going to do this for a final time of 6 seconds. And let's perhaps use a reporting time step, and I'm going to make it coarse so that we can just first look at the actual animation, and then we can run it for the results. I'm just going to use 0.2 seconds in this case. and then I can run anim. Alright, so if I press a key over here in the command window, enlarge this, we can see what happens to the motion of the system. And as we expected, since we're applying a clockwise torque to the rear wheel, the cart is in fact moving from left to right. Okay, so if I'm happy with that, I can then just do a quick clear all, close all CLC. I'm going to rerun DAP now with a finer time step. So still a final time of 6 seconds, but let's perhaps use a 0.01 second reporting time step in this case. It's still going to run for the same number of function evaluations, because remember that the reporting time step differs from the integration time step. So the integration time step is not severely affected by the reporting time step that I am defining on the system. It's still going to run the same number of function evaluations based on its ODE 45 criteria. Okay, so with that now done, I just have to check what the question was. So that was plot the angular velocity of the rear wheel versus time. To do this, I'm just going to type in post so that I can run the post processor. And now I can start by plotting the angular velocity. So I'm just going to call it figure 1 for now. Type in plot, it's going to be versus time. So T is my X label. Then it's going to be PD for all time steps, and I'm interested in body 2 in this case. And let's plot this perhaps as a black line as well. Okay, so I'm going to compare the results to card C, or of card C to card D as well. So what I'm just going to do for now is I'm going to freeze figure 1 in place. So once it has plotted the angular velocity for card C, I'm just going to say hold on, which then ensures that when I now want to plot something else on figure 1, that it's not going to overwrite that plot. It's simply going to keep the current plot that I have and then overlay the new plot on that. And that new plot will then be the angular velocity that we're going to plot for card D. But for now, we can just say hold on. I'm going to hit enter, and then this is the result that I get. So the angular velocity of the wheel then ranges from 0 to just below minus 12 radians per second. And it actually plateaus out over here after about 4 or so seconds to a value which is minus 12 point, it looks like minus 12.5758 perhaps. Now if I go over here and I just type in 4 times pi, then you'll see that's about 12.57 that I get over there. So if I compare this to where this curve plateaus at around 4 seconds, it seems that after about 4 seconds, the maximum torque in the system is reached. Sorry, not the maximum torque, but the maximum angular velocity of the system is reached. And that's why I now get a constant value onwards at around minus 12.57 radians per second. Okay, so then we can see over here as well, the rear wheel or body 2 starts at rest and then reaches the maximum angular velocity of the motor, which is minus 4 pi radians per second. And at this speed, the motor does not provide a torque since there is no resistive load on the vehicle. Now I can also go and plot the velocity of the main body in the x direction versus time. And to do this, I'm now going to call this figure 2. I'm going to plot it versus time again, and when I plot the linear velocities, I use RD. It's going to be for all time steps. It's for the second body, body 2, which is the rear wheel, and it's in the x direction, so coordinate 1 that I'm plotting over there. And I can use a black line for this as well. I'm just going to say hold on as well so that I can compare the results to that of card D. I hit enter, and in this case I can see that the system starts at rest and it now attains a positive velocity. So the card is moving from left to right, and it reaches a maximum velocity of about 1.25 meters per second. Okay. All right, so with that now being said, we can then move on to card D. And in this model, we're going to add a resistive force to the model of card C. We assume that the forward motion of this vehicle is opposed by some sort of an aerodynamic drag that acts on body 1. And we can assume it acts at the center of body 1 as well, so its center of mass. The aerodynamic force can be represented by a simple model as F superscript aero, which is equal to CV square. So C is simply an aerodynamic drag coefficient or a damping coefficient in this case as a function of drag and surface area, and V is the speed of the vehicle. Now I'm just going to head to the editor over here. We can close the input files that we had for card C. And then if I open card D's input files, we can run through them. Okay, so in bodies is going to remain exactly the same. In forces, we still specify weight and then a user-defined force. In functs is still an open list. In joints still consists of the revolute and the disc joints in the system. In points is the 4 points that I use to connect the revolute joints in the system. In U vectors, still an open list since I don't have any translational joints in the system. But now user force has been slightly amended to include the aerodynamic drag force. I don't need to specify two user forces, so I don't need to go to in forces and say F3.type is also user force just to specify the aerodynamic drag. I can combine this with the user-defined force for the actual torque on the system. And all of this will in any case run simultaneously once I run the DAP BC workbench. So as per usual, I specified the motor torque on the system, and now I can simply go and add the aerodynamic resistive force in the system. So I have an aerodynamic damping coefficient of 10. XD is now going to be the velocity of the system, or if you want to, you can use the absolute value, which is going to be the speed of the system, of body 1 specifically. So we say bodies 1 dot RD1. So I'm extracting the X velocity of body 1. And then I can say F aero is equal to damp aero multiplied by XD squared. So regardless of whether I'm using the velocity or the speed in this case, it's in any case going to be squared. So I'm in any case going to end up with a positive value. But I need to account for the sign once I now update the resistive force that is acting on body 1. So to do that, I simply say bodies 1 dot F1 is then equal to whatever the current X force is that is acting on body 1. And now I minus the aerodynamic drag on the system, because aerodynamic drag is a resistive force, so it always opposes the direction of motion of the vehicle, or in this case, the cart. Okay, now with that being said, I'm now going to run DAP, which folder contains the model, and now I'm going to run cart D. Yes, I want to correct the initial conditions, still a final time of 6 seconds, and now I'm going to use a reporting time step of 0.01 seconds. Then I can run post, and now they ask me to go and calculate the angular velocity of the rear wheel and compare these results with the results obtained without the resistive force. And then I also want to plot the velocity of the main body in the x direction versus time and compare this to the results from cart C, which had no resistive force acting on it. Okay, so to do that, I'm now just going to type in fig U in this case. If I hit the up arrow, I can cycle through the previous commands that I entered, which had similar starting commands in this case, or starting letters, characters in this case. So the case that I'm interested in is now figure 1. So I'm going to use this. Now I'm still going to use the same plot. I just want to change now so that I'm working with a red dashed line. And if I'm happy with that, I'm just going to say hold off at the end. So that is then going to give me the output figure with both of the plots overlaid on one another for the angular velocity of the rear wheel. If I hit enter, okay, so in this case, it didn't seem to give me the overlay that I was looking for. All right, so let me perhaps try and rerun the original card again. So card C. Okay, so if I run figure 1, want to plot it again as a black line in this case. And I just have to say hold on over here. Okay, I think it might be because I closed the previous figure, so it cleared the figure in any case. So in this case, I'm just going to leave the figure open, and I'm just going to do figure 2 as well, and leave this figure open. And then I'm going to rerun DAP now for card D. Corrected initial conditions, 6 seconds final time, and a reporting time step of 0.01. I run post, and now I can run figure 1 again. I just make sure to change the line properties over here and then also say hold off. Okay, and now we can see the overlay that we have. So the black line is without any resistive forces, and once I add the aerodynamic drag to the system, so with resistive forces, I can see that my angular velocity now plateaus at a value that is higher than the previous angular velocity. So it aims to damp the angular velocity of the system. If I then look at figure 2 as well, which is then the linear velocity of the system, or of cart body 1. I'm just going to say red line over here and say hold off. And if I open figure 2 over here, I can see that once again, previously I had a maximum velocity of about 1.25 meters per second. Now with aerodynamic drag in the system, I have about 1.16 meters per second. Okay, just a quick change that I want to make, and I realized that now once I typed it in, we are actually interested in body 1. So this should be a 1 over here when we specify RD. We're interested in body 1, or the cart body's linear velocity in the x direction. But it should be more or less the same as what we got when we now used RD2, so the linear velocity of the rear wheel in this case. You're more than welcome to rerun this problem and just check that you get the same results when you use RD1 in this case. Okay, but regardless, we do see the resistive effects on the system. So the results are also shown in figure 8.13 of the PMD textbook, which are then superimposed on the results with no resistive force. And we observe that there is indeed a reduction in the final speed of the cart. All right. So that was then cart D, and also the 2 forward dynamic analyses that we wanted to do on the cart. Now, before we move on to the next example, are there any questions at this stage? Okay, I don't see any questions in the chat messages at this stage. So in that case, we can then move on to example 8.1.4, which is then a conveyor belt and the friction force that we apply on the conveyor belt, how we can model this within the DAP-BC workbench. So this simple example is provided to show how to use a friction model as discussed in section 4.5. So 4.5 deals with friction forces. Before I get to that, just a question. All right, so Mr. Kaya, just with regards to the difference between the hold off and the hold on command. So the hold on command basically freezes your graph in place. So once I have some sort of a plot or a curve that I've plotted on that figure, once I type in hold on, it means that when I plot something else on that figure, it's not going to overwrite the current curve that I have over there. So that is why now in this case I plotted first the curve without resistive forces, I said hold on. So now it locks that curve or freezes that curve on that graph. And then I can now go and plot something else and use it as an overlay on the current graph. And once I'm done with all of the overlays, I can just say hold off at the end. It's not really too necessary to say hold off at the end, but it's just good practice just to make sure that you now unfreeze your graph and that you can now interpret your graph afterwards. But yeah, so just use hold on whenever you have curves that you want to overlay on one another, and once all of the overlays are plotted, just say hold off at the end. That is basically the difference. Okay. All right. So with regards to the friction force, so friction force may be imposed between two contacting bodies to oppose their relative motion. It can be a function of the material of the contacting bodies, the shape and the roughness of the contacting surfaces relative to the velocity, normal force, lubrication, and other factors in the system. So therefore, determining the force caused by all possible forms of friction in one formula is not possible and definitely not very trivial to do. So in general, we rather divide friction into two types. We either have Coulomb friction or viscous friction, or as a combination of the two. So we can consider the two bodies being in contact, as shown in figure 4.11. So 411A shows that we have bodies I and J. We have body I moving at a velocity VI and body J moving at a velocity Vj. And then figure 411b shows the resultant normal and reaction forces that are obtained when I break the system up. So I have equal magnitude but opposite direction normal forces and friction forces acting between the two systems. And we can assume that each body applies a normal force Fn on the other, causing a pair of friction forces, which is known as F superscript F, opposing the relative motion between the two bodies. Okay, so jumping into Coulomb friction, which is also known as dry friction, may exist even if the two surfaces do not move relative to each other. If the relative motion between the two bodies is zero, the Coulomb friction is simply computed as a static friction, which is F superscript F, SF, which indicates that we're working with static friction, and that is equal to mu s times Fn. So mu s is simply the static friction coefficient, and Fn is then the normal force acting on the system. When the relative motion, however, is non-zero, the friction force is then determined as a dynamic friction, and that is what the superscript df indicates. We simply calculate this as mu d times Fn. So mu d is now the dynamic coefficient of friction. So assuming that the dynamic friction is not a function of the relative velocity and the transition from static to dynamic friction is instantaneous, equation 439 and 440 can be represented together graphically and is then shown in figure 4.12a. Right, so in 412a we can see that we have some sort of a static friction in this regime over here, and then there's a sudden jump up to where we have dynamic friction in the system. So we have this mu s and mu s Fn and minus mu d Fn, and then mu d Fn and mu s Fn, which is an instantaneous jump. So it lies on the same line over here, which is on the y-axis. Okay, now with regards to viscous friction, which is also known as wet or lubricated friction, this is now proportional to the relative velocity of the contacting surfaces. So this type of friction can be described in its simplest form as F with superscript Vf, which indicates we're working with viscous friction, is simply equal to mu v times vi comma j, so the relative velocity between the two objects or the two bodies. So mu v is the coefficient of the viscous friction, and vij the magnitude of the relative velocity, which is vi minus vj, or we simply call it the relative speed in the system. If the coefficient of viscous friction is not a constant and is a function of the normal force, then the viscous friction force may be determined in this form over here, where we now work with kv multiplied by vij, and we just multiply by the normal force at the end as well. And kV is another description of the coefficient of viscous friction. So combining all of this, when friction is assumed to be a combination of both Coulomb and viscous frictions, the combined models can be presented as shown in figure 4.12b, whereas the relative velocity increases, so does the friction force. Now, it has been found experimentally that the transition of friction from zero to non-zero relative velocity is not instantaneous, but it takes place over a very short period of time. And usually when we consider an analytical approach, it's a fair assumption to say that it occurs over an instantaneous period of time. But since we're now interested in a more numerical approach, we need to accommodate this shorter period of time. This transition is also known as the Strebeck effect, and this is depicted in figure 412c. So you'll see over here we have minus mu dfn, and then we have this little peak or this little spike over here where it goes over from dynamic to static friction. Now, implementation of Coulomb and viscous frictions, including the Strebeck effect, in the equations of motion of a multibody system is not difficult as long as the relative velocity of the contacting bodies is non-zero. The difficulty, however, arises when these relative velocities are indeed zero, during which the static friction force could be anywhere in the interval from minus mu sfn to mu sfn. So basically anywhere along this line that we plot over here. Now, to remedy this problem, the static friction force can be assumed to vary from minus mu sfn to mu sfn during a short range of varied relative velocities in the vicinity of stiction, as shown in figure 412d. So instead of this minus mu sfn to mu sfn line now lying on the y-axis, we instead have a very short relative velocity span over which the change occurs. And this makes it a bit easier to calculate these values computationally. A variety of analytical formulas to closely represent the force velocity characteristics of the function of figure 412d can then also be found in literature, and the two that we are going to consider is Anderson et al. And then also the study done by Brown et al. So starting with Anderson's study, equation 443 shows the equation that we use to calculate the friction force in this case. So you'll see we have two terms over here. The last term is the viscous friction, which is broken up from the Coulomb friction that we consider in this first part. The general shape of this function is then also shown in this case. So here we can see we have a bit of a rounding over here as it goes from dynamic to static, or into this very short relative speed range over here. Okay, now with regards to that, the viscous friction F superscript Vf in equation 443 can be defined as either equation 441 or 442 that we looked at earlier. In addition to the coefficients of friction and the relative speed, equation 443 also contains some other parameters, and each of these parameters can change the shape of the function. And we discuss some of these shape changes over here. So firstly, we have the coefficient of sliding speed Vs, which changes the shape of the decay in the Strebeck region, as shown in figure 414a. So for different values of Vs, we can see what the effect is over here. It basically makes this curve less or more gradual across Vij in this case. So a smaller value for this parameter results in a sharper drop from the static to the dynamic friction. Just to show you, Vs is over here used as the denominator when we work with the exponent for this term, this first term in equation 443. Then the exponent P affects the drop from the static to the dynamic friction in a different form, as shown in figure 414b. Okay, so we have different values over here. P is typically greater than 1, and over here we plotted it for values of 1, 2, and 3. And you can see what the effects are on the Strebeck region as well. Now, P is just used as the exponent over here when we calculate the Coulomb friction in the system. And then lastly, figure 414 C shows the effect of the value of KT. So KT is used in this tan H or tan hyperbolic that we have over here. So KT is typically also a large value. So you can see over here, the values plotted greater than 3,000 are shown. So 3,000, 6,000, 10,000. And KT then adjusts the slope of the curve from zero relative speed to the maximum static friction as depicted in 414C. And we should also note that with this friction model, the maximum value of the static friction force does not reach the desired value of mu s Fn. So therefore, we may consider a larger value for mu s to compensate for this shortcoming of the model. Okay, and then just to show you some typical parameters that we use, Vs is typically a very small value. So you can see over here 0.001 meters per second sliding speed. P is equal to 2, so it's usually greater than 1. And then KT is also relatively large value, so around 10,000 or anywhere 3,000, 6,000 upwards. So in the thousands over there when we work with that value. So a large value for KT makes the slope of the curve in the static friction region more vertical. Okay, then another example of an analytical formula velocity characteristics of the function of figure 412D is then shown by Brown et al. Okay, and in this case, we have equation 444 that we're working with. So we once again have a Coulomb friction part over here, and then we have the viscous friction over here. And then we also have VR, which is simply a ratio of the relative speed divided by this Vt, which is then known as a transition velocity in the system, indicating the velocity at which the friction force reaches its maximum value and the transition from the static to the dynamic region begins. Now, typical representations of the friction model of equation 444 for different values of the parameter Vt, so the transition velocity, are shown in 415 over here. We can see once again the transition velocity is also a very small value. We start over here with 0.0005 and it goes up to about 0.001 meters per second that we plotted for. Now the model also suggests that the viscous friction FVF should be represented in this form over here, where the parameter Fnt is then called the transition force, and that specifies the required minimum normal force for viscous friction to take place. However, the viscous friction in this formula can also be defined either as equation 441 or 442. It's up to us, but one of the models that we have available to us within the DAP-BC workbench, specifically this Brown et al. Model, so friction model B, already compensates for the viscous friction using this equation that we have available. So it makes it a bit easier to apply when we're doing a quick calculation within DAP-BC. Okay, so that was then the friction analysis that we ran through. Now, if we go back to the original friction model discussion, we can also say that the friction model can be considered between bodies of different shapes, such as the example shown in figure 416. So in this case, we have two solid contact bodies that are sliding relative to one another. In case B, we have body I, which is now a very sharp contact or very sharp friction model that we might want to model acting on body J. And then between body I and J, we also have some sort of a disk friction over here. So if the normal force Fn is the result of a contact represented as a penetration model, such models are then discussed in section 11.2, and the friction force could be categorized as a type of an applied force. And we're going to look at a contact model example in our next lecture, but just take note of that as well. However, if the contact is modeled as a constraint, for which a Lagrange multiplier represents the resulting contact force, the corresponding friction could be categorized as a reaction force. And this is case D that we have over here, where we consider the disk joint as an amended form of our friction force model. So the disk joint is a joint, so it imposes constraint equations on the system, and we can go and analyze those constraints as Lagrange multipliers to get our no-slip condition or our friction condition out between the disk and the surface that it's rolling on. Okay, so with that being said, we can then go and look at our conveyor belt example. Now, the spring mass system shown in figure 8.14 is a typical example that has been used in literature for testing and comparing different friction formulas. In this case, we can see that the block rests on a conveyor belt that moves with a constant speed. This is known as x dot conveyor. As the block moves with the belt, it stretches the spring that we have connected to the block and to ground until the force of the spring overcomes the friction force and pulls the block back. And the process is then repeated so that we have this sort of oscillatory motion in the system. For this system, let us also consider the friction model of equation 443 and the following data. So they give us the mass of the block, which is 1 kilograms, the stiffness of the spring is 10 Newton meters, the underformed length of the spring 0.8 meters, gravitational constant 9.81 meters per second squared. Then we have the speed of the conveyor belt as 0.1 meters per second. The static and the dynamic friction coefficients are also given. We have mu, v, p, which are parameters that we use in our model together with kt. And then we also have our sliding speed, which is also used in the model. And that is once again a very small value of 0.001 meters per second. In this model, it is also assumed that the velocity of the block at the initial time is 0. So we start at rest. We note that the normal reaction force on the block is a constant and equal to the weight of the block as well. Now, exercise 8.11 says we then need to simulate the response for the model for 6 seconds. Before we do that, I first want to jump into these two parameters that we're going to specify on the system, which is our point-to-point force or our spring damper force. In this case, it's just a spring force. We don't have any damping on the system. A spring force that we specify between some sort of a grounded point and the center of mass of the block. Now, for this, we can go back to PMD section 4.4.1, which deals with applied forces. And the point-to-point springs are the most commonly used force elements in mechanical systems. We saw this from the suspension example that we also did. And we can assume that the force element in figure 4.7 is a spring that is attached between two bodies. So we have body I and J. We have a spring that is then attached between them. We construct a vector D from point B to A, so between the points that the spring is connected to. And then we can either have a push or a pull motion between these two points over here due to the stiffness and the damping in the spring. The force of the spring is then computed as F superscript S, meaning we're working with a spring force, and that is simply equal to K times delta L in this case. So the difference between the deformed and the underformed length. K is the stiffness, L is the deformed length, L naught is the underformed length of the spring. And the deformed length L is then also determined from equation 423. So we simply vectorize L squared, and that is equal to D transpose multiplied by D. So L, which is the distance between points B and A, is then equal to this D transpose D over here. So we just multiply the vector with itself, and then we end up with a scalar value, which is equal to L squared. The sign convention for a spring force is then defined as positive in tension. So if we're pulling on the spring, we have tension, and that's positive. Negative is then compression or pushing of the spring. So compressing or pushing the spring inward so that it exerts an outward force on each of these two bodies. The forces that the spring applies on the two bodies are then this F on body I superscript S means it's a spring force, which is equal to minus Fs, so the magnitude of the spring force multiplied by some unit vector. And then Fjs is equal to the spring force magnitude multiplied by the unit vector as well. Now, equation 427 is valid in both tension and compression. So if we have tension in the system, we know that the deformed length is greater than the underformed length, and therefore the spring force in equation 426 is positive, so the bodies are pulled towards each other. In compression, the deformed length is smaller than the undeformed length, so therefore the spring force in equation 426 is negative, so that the bodies are pushed away from each other. So that aligns with our sign convention that we specified previously. Okay, now with that being said, we can also look at a translational joint. So remember, since we're working with a conveyor belt over here, it means that this block is resting on some sort of a flat or horizontal surface, meaning that we need to lock its Y translation into place. It's not allowed to move up or down, but it can move left or right. So that tells us that we need to use some sort of a translational or a sliding joint in the mechanism. So as you by now know, a translational joint allows two bodies to slide relative to one another along the axis of the joint, but it doesn't allow translation in the other direction and also not rotation about the plane perpendicular to the plane that we're working in. So to construct a translational joint between bodies I and J, we describe one point and one unit vector along the sliding axis on each body, and this is then shown in figure 7.4a. So we have body J over here, and we need to make sure that we specify UJ and PJ on the same body, which is then body J. Then for body I, which is then connected via a sliding joint, we also need to specify a unit vector UI and PI, of which both are located on body I. And these are then points PI and PJ and unit vectors UI and UJ when we denoted. Vector D is then defined by connecting PI to PJ, and we connected from point PJ to point PI. So that D is equal to RIP minus RJP. The necessary and sufficient conditions for the two bodies not to have relative translation perpendicular to the sliding axis and not to have relative rotation are then obtained by enforcing UJ, UI, and D to remain parallel to one another. And we do this from a vector perspective. So we set up our constraint equations, which means we're working with a translational joint, imposing two constraints on the system. U prime JD, which must be equal to 0, and then uj prime rotated multiplied by ui must also be equal to 0. And this ensures that all of these vectors remain parallel to one another. And if these constraints are then enforced, a sliding joint is formed between the two bodies, and this is then illustrated in figure 7.4b. And we can see in this case D, uj, and ui are all parallel to one another. Okay, now with that being said, we can also just have a quick look at the time derivatives. Once again, this is handled from a computational perspective. You will not be expected to remember these equations and have to write it or derive it by hand. These are all done within a numerical environment. But we can now go and find the time derivative of equation 719, which provides the velocity constraint. The second position constraint, stating that ui and uj must remain parallel, resulted in the constraint phi.i minus phi.j is equal to 0, which implies there is no relative rotation between the two bodies. The Jacobian matrix from the velocity constraints can then be split into two submatrices, as shown in equation 721. And then if we take the time derivative of equation 720, that will yield the acceleration constraints in the system. And the time derivative of the second row of the Jacobian matrix yields all zeros. The time derivative of the first row then becomes these equations, or this matrix that we have over here. And when we multiply this row by the array of velocities, we can take advantage of phi.i equal to phi.j to simplify the array gamma as equation 723 in this case. All of this, once again, done in DAP-BC itself. Okay, so now with the joints and the point-to-point forces defined, we can now go and plot the coordinate of the block in the x direction versus time. Before we do that, let's first run through the actual input files. So I'm just going to clear my workspace over here. I have to also close all of the input files or input scripts that I have for CAR-T, and then I'm going to open CB, which indicates that I'm working with a conveyor belt, and I can open all of its input files as well. Right, so starting off with in bodies, you'll note in this case that I only specify a single body, body 1, which is then the actual box or the crate or object that is being translated on the conveyor belt. I can increase the complexity of the mechanism by also modeling the conveyor belt itself, but it doesn't really make sense since I don't have a lot of information with regards to the conveyor belt. So instead, what I'm going to do is I'm going to use joints to facilitate the left and right motion of the object on the conveyor belt, and then I can go and remove the conveyor belt and just consider the actual normal force and friction force that is acting on this box or on this object that is being translated on the conveyor belt. Right, so I only consider body 1 in this case, with all of its coordinates and masses and velocities given in this case. Then I also have in points. Now, if I quickly look back at the model that I have over here, I'm going to need at least 2 points to facilitate the motion of the cart or the motion of the body in this case. So I'm going to need some sort of a point that I specify then on ground, also a point that I specify on the box itself so that I connect the point-to-point spring in this case. And then I'm also going to need to facilitate the translational joint in this case. Therefore, I also need 2 points and 2 unit vectors in this system. Okay, so to do that, I specify point 1 as the point that is on body 0, so on ground. I give its local coordinates according to that schematic that I have in the mind map. And then for point 2, its body index is going to be 1. And this point is located at the center of mass. So its SP local coordinates are 0, 0. Once this is done, I can then also set up in joints. So in joints is then the translational joint that I'm working with in the system. I define it as a translational type joint. And now you'll remember from the previous examples that we did, we also have IP index, JP index, IU index, and JU index in the system. We need to make sure that IP index and IU index are defined on the same body, and JP index and JU index are defined on the same body. Now, if I also look at this example that I have over here, since my sign convention is that X is to the right and Y is upward, I can say, well, if I want to construct that vector D that is used when I define a spring force in the system or spring in the system, I can also make the vector go from left to right. So I'm going to define my JP index as 0.1 and my IP index as 0.2 in this case. So then vector D is constructed from 0.1 to 0.2. Now, if I look back over here, IP index is indeed 2. If I go over here, I can see that corresponds to P2, which is then defined on body 1. And then if I go back to in joints, JP index is then the first point that I specify, and that point is on body 0. Now I need to go and set up my unit vectors, and I need to make sure that they correspond to the same definition. So IU index now needs to be specified on body 1. JU index needs to be specified on body 0. If I go to the unit vectors over here, I can see that U1 is specified on body 0, so that's fine. And U local is then 1, 0, so it's simply in the X direction. And then the body index for U2 is body 1, U local also 1, 0. And this makes sense if I consider its xi, eta coordinate systems. I know that for a grounded body, its local coordinate system is the global coordinate system. I know that my translation needs to be horizontal, so therefore the unit vector is going to be simply horizontal. That's why I define it as 1, 0. And then in this case, since my xi coordinate system or coordinate axis is aligned with the x coordinate axis, it's also just going to be 1, 0 for its unit vector definition. I specify all of this. Then under in U vectors, I go back to the in joints file and I specify the IU index and the JU index accordingly making sure that the I and J components lie on the same body. Okay, now once this is done, I can also just have a look at infuncts. So this is, I'm not applying any driver constraints on the system, so therefore the funct is an open list. If I then also look at in forces, in this case, I'm first going to define my point-to-point force that I have in the system. Okay, so for the point-to-point force, it's going to be aligned from point P1 to P2. So the 2 points that I specify over here, JP index is 0.1, IP index is 0.2. And then I also have K, L naught, and DC. Damping coefficient is 0. Since I'm only working with a spring, so I only have the spring stiffness and the underformed length of the spring that I specify. My second force type is the weight in the system. And then the third force type is a user-defined force that I need to specify. And this is now where the friction force is going to be modeled. So to facilitate this, I go to the user underscore force file that I have. And I first want to run it with this Anderson et al. Friction model. So I'm going to uncomment these lines, and I'm going to comment out the Brown and McPhee model that I have over here. All right, so what you'll notice is I first give all of the inputs that I received for the problem. So mu d, mu s, mu v, the sliding velocity vs, p, k underscore t, and then fy, which is just the normal force acting on the system. I know that the normal force is simply the, it will just be the mass multiplied by the gravitational constant. The mass of the body is 1 kilograms. So it's 1 multiplied by 9.81, and that's how I get the 9.81 newtons in this case. I then also have the conveyor speed, which is given as 0.1 meters per second. And then I can go and calculate the relative speed, which is then the conveyor speed minus bodies 1 dot rd1, which means I'm extracting the x velocity of body 1. And that then gives me that Vij, or simply the V relative speed between the two bodies. Once this is given, now I can use the friction underscore A model. And to find this model, you can go to, under your workspace over here, you just go to the formulation, expand that, and you'll see there's a forces subfolder over here. If I expand that, you'll see over here I also have friction underscore A. So if I double click on that, you can see what the function is that is being used. And for the Anderson model, you'll notice that only this first part, only the Coulomb friction part is given. So I still need to go and compensate for the viscous friction in the system. But at least Anderson gives me a good model to go and calculate the Coulomb friction in the system. So I can go ahead and calculate that accordingly. And that's what I do over here. So F is simply the friction force without the viscous friction that I'm calculating. So friction underscore A. And now I just need to take note of the order in which I need to give all of the inputs to this function. So I first give mu s, then mu d, then vs, p, kt, v, and finally fn, which is the normal force. I give all of this as input, and then at the end I can simply say, well, the actual friction force is going to be the Coulomb friction force that I now calculated using Anderson, plus this mu v times the relative speed multiplied by the normal force on the system. And now I've compensated for the viscous friction force as well. And that then completely defines the friction force. So now I simply say Fs. I set, or I vectorize the friction component that I calculated. So this is the X friction force. So it's Fx semicolon 0. And at the end, I just have to add this then to the forces that act on body 1. So bodies 1.f is equal to the current body 1 forces that are acting on, well, the current forces that are acting on body 1 plus Fs. Okay, and if I'm happy with that, I can then save this file, can go back to the command window, and I can start running the simulation. So I'm going to type in DAP. I'm using the conveyor belt example. Using the corrected initial conditions, we can see that our system is starting at 0 initial speeds. So this is the same as what we said we want in the mind map. And then they say that I need to simulate the response for the model for 6 seconds. So let's see what happens if I use 6 seconds with a reporting time step of, let's do 0.05 seconds in this case. Okay, so what you'll notice in this case is I'm running a bunch of function evaluations. It's no longer just 160 or 170 function evaluations. From all of these values that are being plotted out, it tells me that I'm going to have a very high number of function evaluations. The reason for this is because the DAP-BC workbench is now taking very small integration time steps when it reaches that stiction phase that I have in the friction forces. So in that case, the integration time steps are smaller so that I get more accurate results. But this is also the nice thing about something like a variable time step integrator, such as the ODE45 that we're using. It's able to vary the time step based on the level of accuracy that I need in the system. So although it's taking very small time steps at the stiction phase, it's going to take larger time steps after and before the stiction phase that I have in the system, which makes it a bit more computationally efficient. Okay, so if I want to animate the system, I can just type in anim, and I can hit a key over here to see what happens to the system. So I can see there's this oscillatory motion of the box moving left and right. So that tells me that my translational joint is working well and that there is indeed some sort of a spring force that is compressing and pulling on the box the entire time. Okay, so if I'm happy with that, I can then just go post. And then it tells me that I need to plot the coordinate of the block in the x direction versus time. So to do this, I'm going to start off with figure 1 again. And now I'm going to say plot. It's going to be the coordinates versus time. So I'm going to say t. And then for the coordinates, I use the R array for all time steps on body 1 in the 1 direction. And I can use, in this case, a black line to show this. And then just to make sure that my results correspond a bit better to what I have in the mind map, I can also use these axis limits that I now specify in the system. So axis 0, 6, 0.5, 1.5. So that means basically it just rescales the axes a bit better so that I get a bit more of a plateaued graph in this case over here. All right. Now to do that, I'm just going to say axis 0, 6, and I think the other two inputs were 0.5 to 1.5. So 0.5, 1.5. I close the square bracket, close the round bracket, enter a semicolon, and then I probably want to compare these results to friction B's model as well. So I'm just going to say hold on. That's going to once again freeze figure 1 in place and freeze any curves that I currently plot on figure 1 in place so that I don't overwrite the curves when I plot the next friction B model. And then I can hit enter. Okay, and I see that these are more or less the same results that I get from the mind map results. Then I can also plot the velocity of the block in the x direction versus time. So to do this, I'm going to call this figure 2. I now plot t, and now I'm using RD for the velocities for all time steps on body 1 in the 1 direction. I'm going to use a black line once again. And if I just look at their axis scaling, it's 0, 6, minus 0.2 to 0.2. Okay, and And then I can just say hold on again. Right, and that then plots figure 2 in this case. So we can see initially the velocity of the block is negative, so that means that the spring is pulling the block back towards it, and it then achieves this parabolic relationship that I have over here until it reaches a zero velocity again, at which point the spring is now completely compressed, and now the spring is starting to push the block away again until I reach the maximum speed, which is then equal to the conveyor speed in this case. And then from there, the block is once again losing velocity and is then being pulled back towards the spring. And this is then an oscillatory motion which takes place periodically. Okay, and then finally, they probably want me to plot the acceleration of the system as well. So to do this, I'm just going to type in Fi, hit the up arrow, and then I can just go and change this so that I'm working with figure 3. And now I'm working with RDD in this case. The axis limit, I also just have to double check, is now -1 to 1 for the y-axis. So minus 1 to 1. And I can hold it on as well so that I can plot friction B's model over it. Okay, so if I hit enter, this is then the acceleration curve that I get. So I can indeed see that there is a region in which I have zero acceleration, so at which point the block is moving at a constant speed, and that is when it's equal to the speed of the conveyor belt, then I have zero acceleration in this case. Okay, so that is then exercise 8.11, which I wanted to consider for friction model A. Then I can also repeat exercise 8.11, but this time I'm going to use friction model B instead of friction A. And now I can assume a transition velocity of 0.001 meters per second, and I can compare the results against those from exercise 8.11. Okay, so to do this, I'm now not going to clear my workspace or anything. I'm just going to type DAP again. Actually, before I do that, I first have to change that I'm actually working with friction model B in this case. So for that, I'm just going to comment out these first lines over here, and I'm going to uncomment the inputs that I give to friction model B. Okay, now the important thing to notice about friction model B is that the viscous friction in this case is indeed included. So you'll see we first have our Coulomb friction, which is this first term over here, plus, and then the second part over here is now the viscous friction. So friction model B already makes it easier for me in the sense that I don't have to worry about calculating it separately once I've obtained the Coulomb friction. Everything is handled in-house in the friction B script that I have available. All right. Then Fs and the body forces are updated in the same fashion. If I'm happy with all of this, I just save the user force input file again. And now I can go to my command window, type in DAP, which folder contains the model. It's the conveyor belt. I want to correct the initial conditions, use a final time of 6 seconds, and a reporting time step of, I think it was previously 0.05 seconds, if I'm not mistaken. Okay, so just also take note that the previous function evaluations was about 33,800. In the case of friction model B, we're going to see what the effect is. In this case, we now get 11,600 function evaluations. So it requires about 3 times less function evaluations to run. It also includes the viscous damp or the viscous friction in this model. So it's already a bit more computationally efficient than what we had for the Anderson model. Now I can just type in post again, and I can now overlay the plots for the coordinates, the velocities, and the accelerations. So if I look at figure 1, I'm now just going to plot it as a red dashed line for friction model B. And in this case, since I don't have any other curves that I want to plot on figure 1, I can now just say hold off at the end. I can hit enter, And now if I expand this a bit, I can see that there are distinct differences between friction models A and B in this case, but not too significant. So either of the two models provide a reasonable estimation to the friction that is actually applied on the box on the conveyor belt. If I then look at figure 2, I'm going to plot it as a red dashed line as well. And I just say hold off, hit enter. And in this case, I can see that the system is able to achieve a bit of a larger speed magnitude in this case than what we had with friction model A. And it also seems that there is a bit of a phase shift in the case where we consider the maximum velocity of the system. Lastly, we can check figure 3 as well. Once again, a red dashed line, and I just hold off at the end, hit enter, and I can once again see that slight phase shift between the two acceleration curves that I obtained between friction models A and B. But from both models, we can see that they do capture the kinematics in more or less the same fashion. There are, of course, going to be discrete differences, but either model seems elaborate and significant enough to capture the friction on the box. All right, so that then also corresponds to everything that we got in the mind map. So you're more than welcome to go and do these exercises on your own as well, and see if you replace some of the Coulomb friction, or sorry, the viscous friction models with equations 441 and 443. What is the result? Do you get more or less the same results? How do they overlay with the previous examples that we've now done? And to sort of form your own opinion with regards to which friction model will work best for your application. All right, so are there any questions at this stage? Okay, I don't see any questions so far in the chat messages. So in that case, I just want to jump over to assignment 1 as well. And I posted last night as well that assignment 1 is now available on ClickUp. Just want to take you through what the expectations are and the instructions of assignment 1 and how I will be marking it. So the idea behind assignment 1 is that you now use DAP BC 12-2022 to simulate some sort of a planar multi-body mechanism of your choice. It is, however, important that the mechanism is not one of the examples for which input files already exist. It needs to be a mechanism that you set up on your own. You are, however, allowed to modify any of the MATLAB files to conform to your mechanism. So the following files need to be submitted on ClickUp. Going to submit in animate, in bodies, in points, in joints, in functs, in forces, in u vectors, so the standard input files, and then also user funct and user force. Now we've covered user force up to now. That is where you specify your own applied force on the system, which is not some sort of a trivial force. User funct is one of the newer utilities that is available in DAP BC 12 but not available in DAP BC 11. In that case, you can now go and define some sort of an applied function, so an applied driver function, which is not one of the function types A, B, or C. You define the function with respect to time, and then you use it in more or less the same fashion as what you would function types A, B, and C when you define your driver constraint. But I'm going to leave that as a self-study option. You're more than welcome to go and look further into how the user function works. But it's not expected of you to use the userfunc.m file for this assignment. Okay, and then any additional MATLAB files that you have modified as well. So, for example, if you modify the post processor to, after you run post, you plot certain graphs out, maybe include that as well, just to show what the actual output commands were. Then you also need to specify or hand in a PDF report of no longer than 10 pages. There's no naming convention when you define the PDF report. I will mark it in any case. It is, However, important that you include, interpret, and validate all the relevant dynamic analyses in your report, since it will be primarily used for the grading of your assignment. And then the hand-in or the deadline is Wednesday, 8 October, midnight. With regards to the rubric that will be used, this is also uploaded on ClickUp, so you can have a look at that as well. The three criteria that you're going to be marked on is firstly the mechanism and the complexity. So did you actually choose a complex multi-body mechanism consisting of 4 or more bodies and or links, and did you utilize different joints in the system? I don't want to see just a bunch of revolute joints in the system. I want to see you be able to use different types of joints like revolute joints, translational joints, disk joints, or if you want to, you can also set up some sort of a composite joint that we also discussed under the McPherson example. And then the proposed dynamics of the system also needs to be non-trivial. Regarding the evaluation of the performed analysis, you are expected to perform both kinematic and dynamic analyses. So I don't want to see just the motion of the system being evaluated. I also want to see you go one step further and actually consider the loading in the system. So did you look at reaction forces or reaction torques? Did you consider the Lagrange multipliers? Did you make use of the Jacobian when calculating the reaction forces and torques in the system? Those kind of things. And then finally, it's just the interpretation of the results as well. So did you provide an actual in-depth interpretation of the results with many visualizations? So did you provide some graphs and outputs with regards to your system? And did you also provide some sort of a validation or a sanity check for the simulation results to make sure that what you get from the simulation does correspond to, let's say, first order principles, like a quick Newton's second law calculation that you did over there? I think if you can handle or assess each of these criteria and set up your mechanism accordingly, then you'll be fine for assignment 1. For those of you who are interested in assignment 2 at this stage, assignment 2 will also require you to set up a multi-body mechanism, and you are more than welcome to use assignment 1's mechanism for assignment 2. But in the case of assignment 2, you're going to do some sort of an optimization on the system. So you're going to have to parameterize the problem, looking at, let's say, reconfigurability of your mechanism or just varying something or a few variables in your system. So if you are interested in using assignment 1's mechanism for assignment 2, keep that in mind at this stage, but don't worry too much about the optimization at this stage. That is still a study theme that we're going to cover a bit later on in the year. It's actually not the next lecture, the lecture after that, we're starting with the optimum design application examples. All right, but that is then an overview of assignment 1. I believe you should have enough time. It's about more than a month's time to complete assignment 1. So that gives you enough time to also work through the next lecture's application examples and to familiarize yourself with all of the different elements that you're going to use in the multi-body mechanism. Okay, are there any questions regarding this? Okay, so in that case, thank you very much, and I'll then see you in the next lecture. Thanks.